Okay, let's continue. Uh, KFC. It's like 9:20. Like, you want KFC this early? You will get big and fat. Okay, we continue now the next chapter then. Next part. Okay, you write this down, please. There it is. Not working. Okay. Capacitance and capacitors. Got that? No. Got it now? Okay. So, the following. Now, before you write anything, let me explain what's happening. Here is a cell, and this here is called a capacitor. And actually, I'll draw it for you. I'll make it a little bit easier. So, what happens here? You have two metal plates, and they're really close together, but they don't touch. And this is actually a capacitor. And what happens here is, when the current goes in here, this plate becomes positive, and then this plate becomes negative. Then what happens is, if you turn off the cell, if you remove the cell, the current will still flow for a short time from the capacitor. So like a capacitor can hold a very small charge, and if the cell is gone, then the charge is released from the capacitor. So usually there's some special material between the plates, but you don't need a special material. In fact, it just works as well if you have two plates really close together. But I don't think there's much more to say. Like, it's two plates close together, and one plate becomes positive, and then one plate becomes negative. And then if you remove the cell, then the current starts to flow for a short time, only a short time. Okay. So can you try and draw this? This is what a capacitor looks like, and that's the symbol for it. So what words in English sound like capacitor? What words in English do you know that sound like capacitor? Capacity. You know this word, capacity? No?
Rapture.
Let me think. Do you know container? Container? Got it? No.
I heard something. Maybe somebody washing their clothes.
Maybe someone washing their clothes?
No, not that.
Okay. went to Cork last Friday? Just you?
Yeah.
Did you like it?
Mhm.
What do you think
No,
of this?
the city was very boring.
Yeah.
There was nothing there.
But boring means small to you, right?
Yeah.
Yeah.
Both actually, because there's nothing there. I
And
mean, just
what were you wanting?
stores. I expected like skyscrapers, like
Skyscrapers.
lots of people.
Cork. No. No, sorry. No skyscrapers in Cork. There's no skyscrapers in Dublin. Were you really expecting skyscrapers? Because if you
I
were, then you'd be very
thought,
disappointed.
isn't it the second biggest city
Yeah,
in Ireland?
yeah.
I mean, I expected to be at least maybe less developed than Dublin, but a lot less developed than Dublin.
True story. Okay, we got this? No. Got this now?
Mhm.
One second.
I need to continue, Grace.
You wait, okay.
Yeah.
Yes.
Mhm.
Okay. When the cell is removed, the charge will release. Even though the cell is removed, a current will still flow for some time. This is what I was saying. Okay. So let's say exactly what a capacitor is. So this is a capacitor. So a capacitor, now it's also called a condenser, but that's a very old word for it. You don't even need to write that down, but I'm just saying if you've got an old physics book, maybe they might call it a condenser. But anyways, we say a capacitor is an electronic device that stores electric energy. That's all it is. Nothing special about it. And it's usually, not always, but usually a small charge. But sometimes it can be a larger charge. Got that? Yep. Now, capacitance. So capacitor and capacitance. So capacitance is what we use to measure how big the capacitor is. So capacitance is the ability to store electric charge. A common device to do this is the capacitor. And the unit for capacitance is the farad. No, not the farad. The farad. The farad. So mathematically the formula is capacitance is the charge the capacitor can hold divided by the voltage around the capacitor. So C is capacitance, Q is charge, and V is voltage around the capacitor. 1 farad is 1 coulomb of charge held per 1 volt. That is, 1 farad is 1 coulomb per volt. Got that? You got this? Okay, so you have this, yeah. Alright. So these are examples of where we see capacitors. So there's a capacitor in this old camera. You press the button, and then you wait, and then flash. Okay. And actually, for these old cameras, you can hear the capacitor. It makes a sound, you know. Does anyone have an old camera where you press the button and you have to wait? No, not anymore. Then maybe like a Polaroid, yeah. So an example which maybe would be more familiar from TV are these things. Defibrillators, yeah. So in the hospital, you can hear them charging up. The capacitor charges up, and then when the doctor presses the button, the charge comes out. Yeah. So this is another example of a capacitor. So this will be a big charge. Huh? He doesn't look too happy. Maybe. Okay. So for example, a flash camera has a small capacitor on it. When you press the button, the capacitor charges up until flash. The value of capacitance is 1500 microfarads and is charged up across a voltage of 380 volts. How much charge is held in the capacitor? Right, so you don't need to write all of this down. What you could do is you can draw it. So what's happening here, I'll try and draw you what's happening. What's wrong? Oh no, it's not, it's too warm.
Yeah, let's put on my jacket.
Right. Okay. So, no, sorry, that's not quite exactly what I wanted. Oh. Right, so what happens here is the switch is closed like this. So then the current flows around, and then this builds up a charge. Okay? So this has a positive charge, and this has a negative charge. Positive, negative. And then what you do is you press the switch down. So you move the switch down here. So now the current starts to flow. Now, yes, it will flow the way it wanted to originally. So the current starts to flow around this way. And that's really how a camera works. And that's how it works in the hospital as well. So first they press the button, so the switch is up.
But why isn't it just automatic? Why do they have to charge things first?
You probably don't want to keep it charged up for safety reasons, because then if you accidentally touch it, it will be quite bad for you. So at the very least it's a safety thing. And I don't know how good or bad it is for the capacitor to be always charged up.
No, well, I mean, like, why can't you just get the power from the main source, like, without the capacitor?
Because what capacitor does is it
Source and then, like, in one
stores
burst
charge,
it
and releases it in one quick burst, in a few milliseconds. Anyways, for this question, the capacitor is 1500 microfarads. Not you see, got me confused now. Farads, not farads, farads, and the voltage is 380 volts. So there's nothing special here. If you want to know what the charge Q is here, the formula is C equals Q over V. So the charge is CV, which would be 1500 times 10 to the minus 6 times 380. Yeah.
Which is the current, which is the charge and which is the capacitor?
The charge is here, this is the capacitor.
Oh, where?
Here,
Here is charge.
charge in capacitor.
Both?
Both?
Yeah.
Yeah, maybe, I'll be a little bit clearer maybe.
Different or is the
I'll be clearer. So what's happening is, the current goes to the left, but the electrons actually move to the right. So what happens is you get lots of electrons here, and there's a charge Q, and this is when the switch is like this. Then you move the switch down, so then this is gone, and then the electrons continue on their journey. Well, I don't want to put arrows in. So then the electrons move around then. Once I close the cells, the electrons come out. They're released. So this is the capacitor and this is the charge Q here. Okay. What am I doing? Going back to my numbers. Oh no, they're gone. Oh well, I'll just write them again. So C equals Q over V, so Q equals CV, so that's 1500 times 10 to the minus 6 times 380. Ah yeah, it's in the question here. What is the charge in the capacitor? You can write the question down if you want. Let me just give you the answer here. The answer is 0.57 coulombs of charge is in the capacitor here when it's charged up. And if you need the question, here it is here. It's a camera.
What is that?
0.57 coulombs. Got this?
Can you go back to the question?
Got this?
No.
No? Yes?
Yeah.
You're finished.
That's right number.
That's okay, I guess.
Maybe I understand
Maybe.
good stuff.
Maybe you do.
I want to
Yeah.
stop here.
Yeah, me too. Me too. Okay, continue.
No, go to the answer. Okay.
Yeah?
Yeah.
Alright. Now what happens when you combine capacitors? So for example, if they're in parallel. So for example, you have one capacitor here and one capacitor here, and this is C1 and this is C2. And what's the total capacitance? In fact, this is like having one capacitor of capacitance C1 plus C2. So that's like the first rule, if you want to write this down. Yeah? Do you know why it adds like this? Because here, if I want the capacitance in total, so let me call it C total. C total would be if this is charge 1 and this is charge 2, it would be charge 1 plus charge 2, because remember when you have charge, it adds together, like I1 and I2 makes I1 plus I2, and the voltage is V. But because they're in parallel, the voltage is, oh well, you could write it like this, Q1 over V plus Q2 over V. But because they're in parallel, the total voltage, V, is the same as the voltage here and the voltage here. So this actually is the same as voltage 1 and voltage 2. They're all the same. V equals V1, which equals V2. So this is C1, and this is C2. So they add together. I mean, you don't need to write this down, but it's maybe good to at least see how I got that formula. Okay. And the reason is, I'm saying remember that the voltages are the same. And the charges add together. So this is the reason why the capacitance works like this. Okay, so you might want to write those three down and then we'll do series. What have you got?
I don't know.
Got this? So the next one is what happens when your capacitors are in series. So this one is a little bit strange. So capacitor here, the two of them together. Now just before I show you that, can you please note here? If this is 0 coulomb and this is 1 coulomb of charge, or let's say 2 coulombs of charge, that's the same as having 1 coulomb here and 3 coulombs on the other one of charge. The difference is 2. Here, what's the difference? 2. And that's, that's the same as having minus 1 coulomb here and 1 coulomb here. The difference in the charge is 2. The difference in the charge is 2. And the difference in the charge is 2.
It's minus.
Here?
What is the higher value on the left?
That's fine.
If it's twofold.
2 and 4. It's the same. So my point is, which way will the charge want to move? So I think it would want to move to the left.
Because it's opposite direction. It's
This here is positive, and here is no charge. It's like negative. Forget about this. I'm just trying to say, often we only care that the charge is different. They're not balanced. Then they start to move. The reason I'm saying that is because if this is charge Q1 and this is charge Q2, they must be equal, because if Q1 was bigger than Q2, it would want to start to move. Because you remember, if you have like a charge here and a charge here, and they're not balanced, maybe they'll start to move. Like for example here, imagine there's some electrons here, and there's some electrons here. So this is negative, this one is positive, this one here is negative, and this one's like a positive. Like a positive, because there's no electrons on it. These must be balanced, because if this positive was bigger than this negative, if there were more electrons here, if this was more, what would happen? It would be pushed to the right. You know, imagine you had a lot of negative here and a little negative here. It wouldn't be balanced. It'd want to move to the right. So what I'm saying here is the Q1 must be the same as the Q2 when they're in series. That the charges must be equal in each capacitor. Okay. Now what's the total charge? What do you think the total charge might be? So this is like one big capacitor.
Q equal Q1 equal Q2.
Very good. The total charge is also the same, because what happens when this starts to move, these two will cancel. This positive and negative will cancel. So you're just left with this negative and this positive, which is the same. But this is the same as this, which is the same as Q1, which is the same as Q2. So in other words, you have in series, Q total is the same as Q1, which is the same as Q2. And the way the capacitance adds together, you have 1 over C equals 1 over C1 plus 1 over C2, which I wrote here. The voltages add together, and they're different, and the charges are constant. Got that? Continue? Yeah, okay. Right, so I have a 100 millifarads and 200 millifarads capacitors, and they're connected to a 10 volt battery. So the first one is they're in parallel. Yeah, so you can write this one down. This is the last example. Now before you do, we're going to do this question in 2 halves. So I just need the A part first, and then we'll do it. It's not as long as it looks. No, really it's not. I promise.
What's next topic?
I don't remember. Physics, I think. Mm. Yeah, got that? Yes? So we'll draw it first. So you have a 100, a 200 and a 10 volt battery. 100 millifarads, 200 millifarads and a 10 volt battery. Amanda, Grace, ready? Yeah. So first question is they're connected in parallel. So that means they look like this. And there's a 10 volt battery here. So this is A part 1, 10 volts. And this is 200 milli, 100 milli. Right, what's the second part I ask you to do?
Calculate total capacitance.
Right, so this one, the total capacitance is C1 plus C2, which is 300 milli. Next,
What is the charge held in total?
in total,
Yeah.
the total charge, would be C total V. Hang on, back up one step. C equals Q over V. So Q total equals C total V, which will equal 300 times 10 to the minus 3 times 10, which is 3 coulombs, isn't it? Yeah. What's part 4?
What is the charge on each capacitor?
Okay, so for each capacitor, the Q, for example, Q1 equals C1V. Now, because they're in parallel, the voltage is the same, it's 10. So this will be Q1, we'll say this is Q1, 200 times 10 to the minus 3 times 10, which is 2 coulombs, and Q2, which is C2V, which is 100 times 10 to the minus 3 times 10, which is 1 coulomb, which isn't a surprise because together they make the total of 3.
What is the voltage around each of the capacitor? It's parallel, so it should be 10.
10. V1 equals V2 equals 10 volts. Got that? Go down?
Yeah.
No? Kaboom. Don't worry, it's not important. Okay, continue. So the next one is exactly the same, except this time you put them in series. So you have 200, 100, and 10 volts. Okay, what was the first question? Oh, that was the first question. What's the second question? Last time, total capacitance. So that's 1 over C equals 1 over C1 plus 1 over C2. So 1 over C equals 3 over 200. So C equals 200 over 3 millifarads. So you get C equals 66.7 millifarads. Okay, what's part 3 did I ask you?
What is the total charge?
Right, so the total charge, Q, equals CV, C total, which would be 66.7 times 10 to the minus 3 times 10, and that comes out as 0.667 coulombs is what I got. Next part?
What is individual charge?
Right, well that one we know, Q1 equals Q2 equals 0.667 coulombs. So is there last part about the voltage? Probably.
Yes, with the voltage and root thing.
Right, the voltage part is a little bit more interesting because if I use C equals Q over V, that means V equals Q over C. So V1 equals Q1 over C1. That's 0.667 over, what was C1? 200? 200 milli. So that's 0.200. So I get 3.33 volts. So actually I should know what the V2 is without having to calculate it. Should be 6.67 volts, because the total needs to make 10. If you want, you can use the formula again, but you'll get 6.67 volts as the answer. Okay, okay. Yeah. Okay. Can I go back to the slides? Yeah. Okay. Deep breath. Take a picture, please. What? What? What?
Send me later.
Okay. Mhm. Good weather for going home. Got this? I can close it?
Yeah. 20 minute break.
No.